Alright, so today we're going to have a look at further proofs using inequalities. And specifically we're going to have a look at the arithmetic mean, geometric mean inequality. So the arithmetic mean is one that we're very familiar with. We call it the average. And of course it's equal to the sum of all of the numbers divided by the number of numbers. The geometric mean is something you probably haven't seen before, and it's equal to the nth root of the product of the numbers. So the numbers must all have the same sign, obviously, because otherwise we can't square root in the real system of numbers, negative numbers. And it's more useful to find it's more useful than the arithmetic mean, our geometric mean, when finding center of scores, as large scores don't really distort the result as much. The harmonic mean is used when finding the average of two or more rates, and it's taken by finding the reciprocal of the sum of the reciprocals, or the mean of the sum of the reciprocals, by dividing n divided by the sum of the reciprocals. Quadratic mean is used for finding standard deviation, and it's equal to the square root of the average of the sum of the squares. Now, the only two that are in the syllabus are the arithmetic and geometric mean. In fact, the arithmetic geometric mean inequality is actually in the syllabus. The other two are not, but they're useful with these questions. Importantly, the arithmetic geometric mean inequality states that the mean of a set of numbers is always or greater than or equal to their geometric mean, with the equality when all numbers are equal. Okay, there are two different methods to solving these and two different types of questions. Number one is starting with the axiom r squared is greater than 0. So if we want to prove something like x squared plus y squared is greater than or equal to 2xy, then we would always start with the axiom x squared minus y squared is greater than 0, or something like that. In other words, we're taking the axiom, the square root of these things, and putting it inside the brackets, because then we can, square it and get rid of the brackets. Sometimes we might want to just start with the arithmetic geometric mean property, the inequality, but we cannot start with it just randomly unless it's been proven in a previous part of the question. And again, sometimes it's easier to prove, instead of a being greater than b, it's easier to prove a minus b is greater than 0. And I spoke about this before. Sometimes it's easier to work backwards on a scrap piece of paper from the conclusion to the original question, and then writing out your solution in a writing booklet in the correct order. So here we're proving the most basic form of this inequality when n is equal to 2. So we are proving that for a and b greater than 0, prove that a plus b on 2 is greater than or equal to the square root of ab, using the sum and difference of the square roots of a and b. Note, the HSC questions will not, I don't think they will not give you this clue. They'll just give you that proof there. So again, we're going to start by looking at this, this type of thing, a plus b, and we've got a square root of a and b here. So we're going to look at a minus b squared is greater than or equal to 0. That is the only thing that we can say, because we know that this is true. We do not know this is true. If we expand that, we get a squared minus 2ab plus b squared is greater than or equal to 0. And if we plus 4ab to both sides, the reason I'm thinking we plus 4ab is because I've got a 2 down here, and if I put the 2 up here and squared it, I'm going to get 4ab. Now we can plus something in inequalities and it still is true. Now this is a plus b squared. Square root equals not 2ab, sorry. We plussed 4ab to both sides. 4 4, square root both sides. And therefore, dividing by 2, nice and easy. Again, it looks hard, but if you start with this axiom, then it's relatively straightforward. Okay, now, we talked about there's 4 methods here. So starting with greater than 0, starting with this thing here, proving with this, or a scrap piece of paper. Now this one, we're going to do it all 4 ways. We're not going to do it, obviously in an exam you're not going to do it all 4 ways, you just need one, but we're just going to show that we can do this many different ways. Alright, so method 1 is to use an axiom that it's greater than 0. Now, the axiom method told us that we have to take the square root of these things. In fact, this one up here, you could have done it like that. You could have started with root a minus root b squared is greater than or equal to 0, and you would have eventually gotten to the same answer. So let's start with the axiom. Root a plus 1 on root a squared is greater than or equal to 0. If we square that, we're going to get a minus 2. I think I said put a minus here. Yep, that was the strategy. We put a minus here. Plus 1 on a. Still greater than 0. And we're done. A plus 1 on a is greater than 2. So that's method 1. Method 2 was plugging it into the equality x plus y on 2 is greater than or equal to the square root of xy. Now again, we can only use this if it's been proven in a previous part. So we're going to say x is a and y is 1 on a. So a plus 1 on a over 2 is greater than or equal to the square root of a times 1 on a. A times 1 on a is 1. So a plus 1 on a timesing the 2 up is greater than or equal to 2. Done. What was method 3? Left-hand side minus right-hand side. So a plus 1 on a minus 2, and we're going to prove that it would be greater than or equal to 0. Now, we've already shown that the expansion of this is that, so we can actually go back the other way and say this is root a plus 1 on root a squared, and if we square something it has to be greater than 0. So therefore a minus 1 on a plus 1 on a minus 2 is greater than or equal to 0. So therefore a plus 1 on a is greater than or equal to 2. Example number 4, we're going to go backwards. So we're going to assume that a plus 1 on a is greater than or equal to 2. We could say that this is a minus 2 plus 1 on a being greater than or equal to 0, and then we can factorize that. Root a plus 1 on root a squared is greater than or equal to 0, and we know that this statement is true, so then we would rewrite it in the correct order. Okay. Example 3, we've got for a, b and c being greater than 0, prove that ac on b plus b on c is greater than or equal to 2 root ab. Okay, let's do the first strategy. We're going to look at the difference of the square roots. Root ac minus root b on c squared, and we know that's greater than or equal to 0. If we square that, we get ac minus 2 root ab plus b on c is greater than or equal to 0, plus the 2 root ab, we get ac plus b on c is greater than or equal to 2 root AB. Done. You also, if you'd proven the arithmetic geometric mean inequality in a previous part, you could have substituted into that and you would get the same answer. Okay, we're going to prove that x is greater than or equal to 2 root x minus 1. Okay. So what we might do is we're trying to prove, so x is greater than or equal to 2 root x minus 1. Now, it's not really in a form that we're familiar with because I don't have anything after this. I've only got an x on the left-hand side. Usually I've got two things. So what we might do is say that this is the same as x plus 1 minus 1. Now, it doesn't have to be plus 1 minus 1. It could be plus 7 minus 7. And now we can use the strategy. So the square root of the first thing. So actually, and then again, that's going to be a problem because we can't square root minus 1. So what we might do, we could write it as x minus 1 plus 1. 2 root x minus 1. And then we could do it. Root x minus 1 plus 1 squared. And we know that's greater than 0. If we expand that, we're going to get x minus 1. I think we want the difference, so we're going to put a minus here. I'm not a fan of this method for this question. I might show the other one as well. X minus 1 minus 2 root x minus 1 plus 1, that's greater than 0. So therefore, x minus 1 plus 1 is greater than or equal to 2 root x minus 1. So therefore, x is greater than or equal to 2 root x minus 1. We might as well do it by method 2 again. So method 2, we're going to say let x plus y on 2 be greater than or equal to the square root of xy. So that's our geometric arithmetic mean inequality. And we might sub x equals x minus 1 and y is equal to 1 into this. So x minus 1 plus 1 on 2 is greater than or equal to the square root of x minus 1 times 1. So therefore x on 2 is greater than or equal to the square root of x minus 1. So x is greater than or equal to 2 root x minus 1. I prefer that method there for this question. Okay, example number 5, we've got for a and b being greater than 0, prove that a plus b squared is greater than or equal to 4ab. This question, I'm thinking, we might have a look at the left-hand side minus the right-hand side. We want to prove, we might go, left-hand side minus right-hand side is greater than 0. You probably could do it the other two ways, but I'm thinking that's going to be the easiest here. So a plus b squared minus 4ab. If we expand that, we're going to get a squared plus 2ab plus b squared minus 4ab. And that is equal to a squared minus 2ab plus b squared, which of course is a perfect square. So that's a minus b squared. And a minus b squared has to be greater than 0 because if you square any real number, you get a number greater than 0. So therefore, a plus b squared minus 4ab is greater than 0, and we've proved that a plus b squared is greater than or equal to 4ab QED. Right, example 6, we've got given that a plus b on 2 is greater than or equal to root ab, prove that x on y on xy on z plus yz on x plus zy on x is greater than or equal to x plus y plus z. In this question, we are given this thing here, so it's looking like we're going to use method 2 here. So we're going to substitute in our two things. So what we might do, what we've got is, we might have a look at we've got 3 things here, but we've only got 2 things that we can substitute into our inequality. So what would be easiest to do here is we might say that xy on z plus yz on x over 2 is greater than or equal to the square root of, if we multiply those two together, we're going to get xy squared z on zx. And if we simplify that, we're going to get 1 on 2 xy on z plus yz on x is greater than or equal to y. Now, I've only substituted in 2 out of 3 of these, which is a problem because we've got 3 of them. So what we're going to do here is we're going to substitute 2 out of 3, but there's many combinations of this that we can do. So I've substituted in this one and this one, but we also need to substitute in separately this one, and also that one and that one. Now if you do that, we might call this equation 1. If you substitute in this one and this one into this inequality, you get 1/2 xy on, no you don't, you get 1/2 yz on x plus zx on y, but this time it's going to be actually greater than or equal to z. And finally, if you substitute in this one and this one, you get 1/2 xy on z plus zx on y being greater than or equal to x. We call this 2 and 3. Now if we add these together, we get 1/2 xy on z plus yz on x plus 1/2 yz on x plus zx on y plus 1/2 xy on z plus zx on y being greater than or equal to x plus y plus z. Now if we times both sides by 2, well this half is going to go away, so we might say this is equal to, let me just copy this, make it a bit smaller. Now we're saying this side is greater or equal to the x plus y plus z, so it's bigger than it. So if there's all halves here and we multiply it by 2, it's still going to be greater because 2 is making it bigger again. So it's still greater, so we're done. Okay, proving using 3 or 4 variables. Now, we can, it's a bit harder, but we can prove this inequality and use using the inequality to prove things involving more than 2 variables, such as a, b, c, and d. Now, there are 2 methods. And first method we're going to do is substitute the arithmetic mean for a and b and the arithmetic mean for c and d into the AMGM inequality for 2 variables and prove the result for 4 variables. Or we can substitute in the mean of a and b and c for d in the AMGM for 4 variables and prove it for 3 variables, which is what we just did in the previous question. Okay, so first of all, we're going to prove that a plus b plus c, a plus b plus c plus d on 4 is greater than or equal to the 4th root of a, b, c, d. Okay, so the best solution for this is to substitute the arithmetic mean for the first two variables and the last two variables into the inequality. So we're going to substitute in x being a plus b on 2 and y being c plus d on 2 into x plus y on 2 being greater than or equal to root xy. So a plus b on 2 plus c plus d on 2 over 2 is greater than or equal to the square root of a plus b on 2 plus c plus d on 2. And we can say that this is equal to a plus b plus c plus d. The 2 will go down to the bottom, it will make that a 4. And we can say this is greater than or equal to, well, we know that a plus b on 2 is greater than or equal to the square root of ab. And we know c plus d on 2 is greater than or equal to the square root of ab. So if this is greater than that, and this is less than that, then we can say that this is root AB plus a times by, that should be a times there, Tom, times by root, and that's a CD there, God, times by CD, and that's because this is less than this, and this is less than that. So if I replaced that with this, it's still going to be less than that, which means this is still greater than that. Now if you take the square root of a square root, you get the 4th root, so therefore this is a plus b plus c plus d on 4 is greater than or equal to the 4th root of a, b, c, d. Done. Again, these are starting to get quite tricky, but it's something we're going to focus and spend quite a bit of time on. Okay, if a, b, c, and d are greater than 0, then prove that a on b plus b on c plus c on d plus d on a is greater than 4. Okay, we're just going to substitute all of these into the inequality. So the inequality states that a on b, we're going to go plus b on c plus c on d plus d on a over 4. Actually, I've done a few steps in one in my answers. Over, over 4 is greater than or equal to the 4th root of a on b times b on c times c on d times d on a. So I've just substituted all of those things into the inequality. Now, we know that a, b, c, and d, we can actually cancel. They're greater than 0. We also know that we can cancel all of these. So that's just 1 there. So a on b plus b on c plus c on d plus d on a is greater than or equal to 1. That's all over 4. So therefore, a on b plus b on c plus c on d plus d on a is greater than or equal to 4. We're done.